I am so excited to welcome Elaine Shi from Cornell University and the co-founder of IC3. She's the co-inventor of Thunder's core consensus protocol and co-author of the first peer-reviewed publication on Bitcoin and the first peer-reviewed publication on smart contracts. Professor Shi will be talking about Thunder.
Thank you so much for the introduction. I'm very happy to be here. And today I'm going to be talking about Thunder token, and a very fast and high throughput blockchain that our team is building. You can think of it as a much faster version of Ethereum. We are going to be EVM compatible. Okay, so 2017 is said to be the year of the ICO, and 2018 is the year of the DApp. Right? There are many exciting DApps. There's games on blockchains like CryptoKitty. There's sharing economy, like putting Uber and Airbnb on top of blockchains. There are many others, like prediction markets, decentralized exchanges, social networks, so on and so forth. Okay, so all of this is very exciting, but there is a truth that everyone knows, but no one likes admitting. That is, none of these apps will actually take off to a large scale on top of today's blockchains. They're just too slow for the purpose of all these DApps. For instance, this chart shows Ethereum transaction fees over time. If you look at it carefully, in December last year was a particularly exciting time for our community, partly because CryptoKitties also came about in December, right? If you compare CryptoKitties with traditional games like social network games, mobile games, it's not like they have a lot of volume, but the single game alone was sufficient to overload the entire Ethereum. So back in December, Ethereum transaction fees were like $1 million USD per day, and Ethereum was like 90% utilized back then. So this is a big problem. Okay, now scalability, as I said, I believe is the most exciting and a very challenging problem for our community today. In our company, Thunder Token, we believe that we have the best technology to overcome this challenge. And even with a single shard, we can achieve 100x more throughput than today's blockchains, and we can confirm transactions in less than a second. So now, in today's talk, I'm going to focus on describing the core consensus protocol that enables such a fast cryptocurrency. It's called Thunderella. This is joint work with Rafael Paz. Of course, it takes a lot more than just the consensus protocol to build a new cryptocurrency. Like, for instance, we have to have the right incentive mechanisms. We have to have the right governance policy. But in the interest of time, today I'm only going to focus on the consensus protocol. Okay, and if you guys have any questions, please feel free to interrupt me. So to explain consensus, we first have to understand that what problem we are trying to solve. So the problem we are trying to solve here is called state-machine replication. It's also called linearly ordered log or consensus. In the rest of the talk, all these terms roughly mean the same thing. Okay, so what is state-machine replication? Imagine we have a set of servers. In this case, we have Google Wallet servers. Now, the job of Google Wallet, of course, is to establish a linearly ordered log of transactions. And the transaction log will grow over time. And there are two important properties that we care about, namely consistency and liveness. Consistency says that all the honest nodes must agree on the log. Now, the network may have delay, right? So it could be that your log is a little faster than mine. That's okay, but it must be the case that your log is a prefix of mine or mine of yours. So now the second property is liveness. Liveness says that whenever an honest client submits a transaction, very soon the transaction will appear in every honest server's log, right? It's not like we want to wait forever for our coffee. So at first sight, this seems like a very boring problem. What is so difficult about building a linearly ordered log? Indeed, if all the servers are honest and they correctly follow the protocol, this indeed would have been a trivial problem. But what's non-trivial about it is when some of these servers can be corrupt. For example, some of these servers can have malware, and the malware can be exploited by the adversary. And these corrupt servers can deviate arbitrarily from the honest protocol. And even in these situations, we want to make sure that the remaining set of honest servers still satisfy these security properties. So that's why this is a very challenging problem. As it turns out, state-machine replication is not a new problem. It has been around for 30 years, and the distributed systems community have been working on this for a long time. And in fact, if you look at all these companies in the Silicon Valley, everyone actually deploys some state machine replication protocol to replicate their computing infrastructure. So for instance, Apache Zookeeper is an open source implementation of Paxos, right? Paxos is a state machine replication protocol, and many of these companies deploy Apache Zookeeper. Okay. Traditionally, when we talk about consensus, the kind of scenario that we have in our mind is exactly what I talked about. There's a single company like Google or Facebook, and they have, let's say, 12 nodes, and these nodes are connected with fast local area network. Okay, so like I said, consensus is not a new problem, but what is new here is the large scale. With cryptocurrency, what is amazing is that we are now having consensus on the internet scale involving thousands to millions of nodes. And as it turns out, consensus on a large scale is very much a different beast. It is much, much more challenging than the classical setting. And this perhaps explains why all these ICOs out there, everyone's rushing to create and invent their own consensus protocol. But at the end of the day, this doesn't make any sense, right? Just like crypto, consensus is very tricky as well. And we know that you shouldn't be rolling your own crypto implementation. So why is it the case that everyone feels the need to invent and roll their own consensus implementation? Okay, in the rest of the talk, I'm going to try to answer these two questions. Number one, like I said, why even after 30 years of research and development, there still isn't a dream large-scale consensus protocol? And number two, I'm going to explain what I believe to be the dream large-scale consensus. Okay, so let's begin with number one. To understand why there still isn't a dream protocol, we need to look at the consensus landscape. So roughly speaking, there are two broad classes of approaches, and I'm going to call them the classical approach and the blockchain approach. So classical approach, typical examples are like PBFT and Paxos. These are the kind of protocols that Google and Facebook deploy. So what do we know about classical consensus? When the network has sufficient bandwidth, these protocols are very fast because they can confirm transactions in the normal case in constant number of round trips. On the other hand, these protocols are notoriously complex, and this makes these protocols very difficult to implement, to do security audit for, and to maintain. And also, you may have heard that these protocols, they don't scale very well to a large number of nodes. Okay, so then there is blockchains. Blockchain is, the modern, the more sexy approach, right? And the first blockchain, of course, is Nakamoto, which is the protocol that underlies Bitcoin. Okay, so what is amazing about blockchain is that, as it turns out, they're not just an empirical success. Blockchain-style consensus is actually a mathematical breakthrough because now that we understand the mathematics behind blockchains, we know that blockchain's mathematics kind of completely departs from classical. Okay. And so what are the advantages of blockchain-style consensus? First, they're very simple, right? The protocol rule is that everyone looks for the longest chain and they try to extend the longest chain by mining the next block. And these protocols have been empirically proven to be robust on a large scale, and we actually now can also articulate some of these robustness properties mathematically. Okay, but the biggest drawback of blockchain-style consensus is that they're very slow, right? As you know, Bitcoin takes 10 minutes per block. And if you want to have sufficient confidence, you should wait for 6 blocks, which is like an hour, right? You have to wait for an hour for your coffee. And another complaint about blockchains is that they waste a lot of energy, right? People have to solve computational puzzles. But for the purpose of this talk, I'm going to ask you to take a leap of faith and believe that the energy waste problem is already solved. Like, for instance, there has been quite a few works that show how to instead rely on proof-of-stake assumptions to build blockchain-style consensus, and meanwhile, we can precisely emulate the mathematics behind Nakamoto's blockchain. So in the rest of the talk, whenever I mention blockchains, it can be proof of work, it can be proof of stake. Okay, so of course, this is the landscape, and again, the question we are trying to solve is, what is the dream large-scale consensus protocol? And obviously, classical blockchains, neither of them will address our need. Okay, so I'm going to try to answer this question in the remainder of the talk. And the plan is the following. I'm going to start with classical. I will explain how classical consensus works. And in the middle, I will get stuck. When I get stuck, I will try to combine the best of both worlds. So let's begin with classical. And here's our scenario. In this scenario, we have a leader who's Vitalik. Vitalik is the founder of Ethereum. And we have a committee of stakeholders. So in this case, the stakeholders are superheroes. Okay, so now these committee are going to be the voters, right? Some of these voters can be corrupt, like in this case, Loki is corrupt. And of course, the leader can also be corrupt. Okay, so what I'm going to explain is a very simple voting-based protocol, and I want us to think together what properties this protocol can achieve and what it cannot achieve. Okay, so let me describe the protocol first. Step number 1, the leader is going to make a proposal. The proposal contains the sequence number and a batch of transactions you want to confirm. So for simplicity, I'm also going to call this a single transaction, but in practice, you want to confirm a batch at a time. Okay, so the sequence number, what does the sequence number do? Right? Remember, we are building a linearly ordered log in the end, and the sequence number is going to determine where in the log this transaction will land. So in our entire protocol, we need to run many little instances of this little voting protocol, but for the time being, we are going to focus on one single instance. Okay, so leader makes proposal. Step number 2, everyone's going to vote. Remember, in this case, Vitalik proposed a golden transaction, and if you are honest, you will vote precisely for the golden transaction. But of course, in this case, Loki is corrupt, so he didn't follow the protocol. Instead, he voted for a blue transaction and a red. Okay, so what do we do now? Now we wait. We wait until we hear enough votes on the same transaction, and once we hear enough votes on the same transaction, we can confirm and output the transaction. So very simple, 3-step voting-based protocol. And the most important thing to remember about this protocol is that the honest nodes are going to vote uniquely. If I'm honest, I'm going to wait until the leader makes the first proposal for every sequence number, and I'm going to vote on that proposal and only that proposal. Okay, so by the way, a vote is a signature on the transaction that's being proposed by the leader. Okay, so with this in mind, I'm going to give you a very simple consistency proof. And to understand the consistency proof, let me describe the parameters first. So we are going to assume that less than 1/3 of the committee are corrupt. So n is the total number of nodes, and less than 1/3 of them are corrupt. And in this case, I claim we only have to wait for 2/3 of the people to vote. Once I collect 2/3 votes, I can confirm. And here's why this protocol gives you consistency. Imagine in this case, Spider-Man has heard 2/3 of the people voting for the red transaction, and Iron Man has heard 2/3 of the people voting for the orange transaction. Now, if you do the math, because of the very simple pigeonhole principle, the intersection of the red set and the orange set of people, this intersection must contain at least one honest node. So it's a very simple pigeonhole principle, nothing fancy about it. But remember that honest guy is going to vote uniquely, that honest guy in the intersection. And that is why the red transaction must be equal to the orange. And in this consistency proof, notice that the only thing it relies on is the fact that honest nodes vote uniquely, and we never relied on the fact that the leader's honest. Okay, so keep that in mind. And let's think about what this very simple protocol can give us. But we are going to look at it from 2 different worlds. We have the world when Vitalik is honest and the world when Vitalik is corrupt. When Vitalik is honest, things are all good. We have consistency, as I've just proven to you. And we also have liveness, because when Vitalik is honest, he is going to propose the same transaction to everyone. And soon enough, you are going to collect enough votes, right? Because 2/3 of the people are honest. And then you make progress. But what happens when Vitalik is corrupt? As I said, we still have consistency in this case, because the consistency proof never relied on the fact that the leader is honest. But we don't have liveness. Because, for instance, if Vitalik is corrupt, right, he can simply just crash and not make any proposals. And he can also propose different things to different people. And in this case, everyone's going to end up voting for a different thing. And you can wait, and there's never enough votes for the same transaction. So you get stuck from that point on. Okay. So at this moment, it seems like the crux of the problem is that we have to solve the liveness issue when the leader is corrupt. And if we can do that, then everything will be good. Okay. Unfortunately, this problem is not easy. If you look at all these classical protocols like PBFT, Paxos, they resort to a very complicated recovery path to solve the liveness issue when the leader is corrupt. And I don't want to have to explain how this works. So let's kind of take a step back and look at how most of these classical protocols work. And they actually share a very similar structure. There's a very simple normal path consisting of one or more rounds of the voting protocol I mentioned. But when the normal path fails, you fall back to a very complicated recovery path. And if you look at this picture, you want that most of the time, the system is operating in the green part. But then again, if you look at the code, most of the code actually is in this red part. And that's where all the bugs and complexity are. So that's not very desirable from a systems perspective. And what does this complexity mean in practice? Like, for instance, Chain.com is a San Francisco-based company. They're rolling blockchain solutions for Visa. And they basically completely gave up on this implementing the recovery path. And what this means is that when this normal path fails, they have to fix the problem manually, which means they have to do all this red stuff manually. And imagine if this protocol is deployed among 100 banks, and you have to basically go to all of these banks, sync their logs, and rebootstrap the protocol. And that's going to be really painful in practice. OK. So at this moment, we are kind of stuck. But as I promised, when we get stuck, we are going to try to combine the best of both worlds. So our idea is very simple. This is classical. We ditch all this complicated red stuff. We replace it with a very simple blockchain. And that's the high-level idea behind Thunderella. I will explain to you how to instantiate this idea in a provably correct manner. But before that, I want to say, I'm also going to call the fast path and the slow chain. Right? The slow chain can be Ethereum, can be Bitcoin, but it can also be a proof-of-stake blockchain. OK. And here are the goals that we want to achieve. We want that almost all the time, the system is actually operating in the fast path. And in the fast path, we can confirm transactions in 2 to 3 actual network round trips. You don't have to wait even for a single block interval. And in the fast path, we also rarely have to use the slow chain at all. Like that's why we get very high throughput. But when you're under attack and when things are not so good, that's not the end of the world. Because in the worst case, we fall back to the security and performance of today's blockchain. OK, so that's what we can achieve. Before I describe the protocol, let's recap the scenario. We have an underlying blockchain. For now, you can think of it as Ethereum, but it can also be proof-of-stake blockchain. We have a leader and we have a committee. I'm going to ask you to take a leap of faith and imagine that there's a mechanism to elect the leader and the committee. And both the leader and the committee can evolve over time. So I won't describe in detail how these are elected. For instance, they can be elected through stake, right? And to get our worst-case security guarantees, we have to assume that the blockchain is secure. And if this is proof-of-work blockchain, we have to assume majority of the mining power is honest. If it's proof-of-stake, we have to assume majority of the stake is honest. We are also going to assume that the majority of the committee are honest as well. But we don't have to assume anything about the leader. Even if the leader is corrupt, it doesn't break the security of the scheme. OK. Now, I will first describe the fast path. But I kind of already described it before. At this moment, I'm going to focus on what happens when there are many of these little instances for different sequence numbers. Right? So remember, the protocol is that the leader makes a proposal, everyone votes. So now there are many of these sequence numbers, and I'm going to introduce a notion called notarized. If any transaction has collected 3/4 votes, I'm going to call that notarized. So the threshold has changed here a little bit because we are assuming majority honest now. Earlier, we are assuming 2/3 honest. So for majority honest, to get the consistency argument to work, you have to have 3/4 votes. Okay, so now, in this picture, 1, 2, and 3 have been notarized, 4 is missing, and 5 and 6 are notarized too. In a cryptocurrency system, it is very important that you process the transactions in a linear order. Because, for instance, 4 and 5 can be conflicting transactions that try to spend the same coin, and we want to prevent double spending here. In this case, the only transactions we can process is 1, 2, 3. And for the lack of a better term, I'm going to call this the maximal lucky sequence. You can confirm and output the maximal lucky sequence. All right? So this is basically the fast path algorithm. And remember, the problem we need to address is when the leader is corrupt, we have to solve the liveness issue. So how do we do that? Well, so far, we haven't used the slowchain at all, right? We have to use the slowchain somehow. And that's how we are going to address the liveness issue. And how do we use the slowchain? We use it for 2 different purposes. First, we are going to use the slowchain to detect when the fast path has failed. And once the fast path has failed, and we detect that, we want to initiate a fallback procedure and fall back to the slow chain. So in this slow mode, people can still post transactions to the slow chain and have them confirmed on the slow chain. Things are a little slower, but the system doesn't stop. And when you are in the slow mode, you can always rebootstrap the fast path. Okay, so that's what I'm going to explain. I will explain, number 1, how to do this detection, and number 2, how to do the fallback. So first, how to do the detection. The challenge here is that we need a robust mechanism, a mechanism in which faulty nodes cannot implicate an honest leader, because we want to prevent denial of service. Okay, so here's a very simple idea. Imagine when the protocol is operating normally, the committee posts notarized heartbeats to the slow chain. So a heartbeat contains a hash of the fast path log so far. And then all the committee members are going to sign this hash. And then when this hash becomes notarized, you post it to the slow chain. So every now and then, you keep posting these heartbeats. And these heartbeats also serve as a checkpoint of the current fast path. Okay, so normally, as you can see, in normal mode, we barely have to use the slow chain at all. And the only way we are using the slow chain is to post these periodic heartbeats. Okay, so imagine at some point, I observe that k blocks have gone by without a heartbeat. So this looks suspicious, right? So k in this case is a security parameter. You can imagine k to be 6 for Bitcoin, and k is, let's say, 300 for Ethereum. So the heartbeats have been missing, and what could have caused this, right? So for instance, if the leader has crashed and is not making proposals, this can happen. If the leader is censoring transactions and the committee want to vote the leader out, they can also refuse to sign. And in all of these cases, the heartbeat is missing. And when this happens, we want to fall back to the slow chain. So I have to tell you how to fall back in a provably secure manner. And to understand how to do the fallback, let me try to explain the problem here. Right? The problem is we can all decide that we want to fall back, but at this moment, our fast path log can be different. Like for instance, in this case, Spider-Man's network is a little slower. So he believes the fast path log ends at 3, whereas Iron Man believes it ends at 6. And at this moment, they all want to fall back. It is important that they reach agreement on what the fast path log is before falling back to the slow chain, right? Because once you are in the slow chain, you post transactions to the slow chain to confirm, and that's appended to the fast path log. How do we reach this agreement? If you think about it for 5 minutes, you'll realize this is an agreement problem in itself. Like earlier, we punted on the liveness issue, but here we can no longer punt on liveness. We have to have an agreement mechanism that's both consistent and live. And how do we do this? Again, we use the underlying slow chain for help, right? The slow chain is kind of like a very robust mechanism, consensus mechanism that's always there. It's sure and steady, but it's just, it's a little slow. Okay, So now the fast path has failed, and the nodes are going to use the slow chain to communicate to reach consensus on where the fast path log ends. And the way you do it is the following. First, when we want to fall back, we stop participating in the fast path. We stop signing. Number two, we are going to tell each other the notarized transactions we have seen. And number three, we are going to post all the notarized but uncheckpointed transactions to the slow chain. So if the transaction has been confirmed by some heartbeat on the slow chain, then it's checkpointed. But we are going to post basically all the notarized but uncheckpointed transactions to the slow chain. You are going to keep doing this for k number of blocks, where k is, again, a security parameter, like 300 for Ethereum. And by the end of the grace period, we basically reach agreement on where the fast path log ends. And one subtlety here is that if I have confirmed some transaction earlier, I don't want it to roll back by the end of the grace period. But we can guarantee this because the maximal lucky sequence contained in the slow chain by the end of the grace period is at least as long as everyone's fast path log when we started the grace period. So this is something we can prove. All right. So that's basically the protocol. To summarize, the way we address the liveness issue is to use the slow chain to detect fast path failure. And when we have detected failure, we fall back to the slow chain. And in the slow mode, you can always try to rebootstrap the fast path. OK, and to quickly recap the properties we can achieve, right? To get worst case security guarantees, we only need to assume majority honest. And I want to stress that we don't have to assume anything about the leader for worst case security, because even if the leader is arbitrarily malicious, the only thing it can do is to slow down the protocol. It cannot break consistency. It cannot cause the protocol to stop either. So that's actually, even though it may seem like we have a central point in the protocol is actually fundamentally decentralized in terms of security. OK, so now, when things are good, we can be fast. And what do I mean when I say things are good? If, let's say, 3/4 of the committee are online and honest, and if the leader is also online and honest, then things are all good, and we can confirm transactions very fast. Everything's on the fast path. OK, to recap the protocol, here are the 2 sentences you have to remember to reconstruct the protocol yourself after this conference. When things are good, we perform a single round of voting in the fast path. And when things are bad, we use the slow chain for fallback. And when you are in the slow mode, you can always rebootstrap the fast path. So that's Thunderella. And I've skipped a lot of these details, like how to elect committee, how to elect the leader. There are a bunch of practical optimizations that we do, which I kind of skipped for simplicity. In our paper, we also have formal proofs of security. So this is not proof of work. This is like security proofs. I've been asked what is proof of security. All right. OK, before I end, I want to describe some of these insights we have gained, right? So in particular, why after 30 years of work, we can claim to be a lot simpler and faster than everyone else. There has to be some insights here. OK, now, if you look at all these classical protocols, they work in what's called an asynchronous model. So what is an asynchronous protocol? An asynchronous protocol doesn't know how long it takes to deliver messages. In other words, the same protocol has to work no matter how long it takes to deliver messages. As it turns out, if you have worked in distributed systems at all, asynchrony makes life a lot harder. So that's why these classical protocols are very complex. In comparison, we kind of baited and switched. We switched the underlying protocol to a synchronous one. So what I'm saying here is blockchains are synchronous protocols. And that's why, in comparison with asynchronous, a synchronous protocol is allowed to know the maximum network delay. And because of this extra assumption, these protocols can be simpler than asynchronous protocols. So blockchains are synchronous because we have to parameterize the block interval. And there are mathematical proofs that show, if you want to resist 49% attack, the block interval has to be like 60 times the maximum network delay. And that's why the protocol needs to know the maximum network delay. All right. So you may ask, why earlier people didn't use synchronous protocols? Like why this is, synchronous protocols are only used today for large scale. There is actually a reason for this, because in the classical Google, Facebook scenario, they want to achieve, let's say, microsecond to millisecond latency. And then people tend to believe that these synchronous protocols are slow, because like in these cases, you don't want to even wait for a single block interval or a single synchronization round. But what we show is this classical wisdom is kind of not correct. Like we show that you can be a synchronous protocol and you can still be fast. So if you look at Thunderella, most of the time it's operating in the asynchronous land, and that's why we are fast. But fundamentally, we are a synchronous protocol, and that's why we are simple. So this is basically a new paradigm for designing consensus. And this new paradigm is actually very powerful, even from a theoretical perspective. So now putting my theory hat on, right? So earlier we know that if you want to work with asynchrony directly, there are a bunch of these lower bounds. For instance, one of these lower bounds says that an asynchronous protocol cannot tolerate more than 1/3 corruption. So in some sense, this is saying that if you want to be fast, you cannot tolerate more than 1/3 corruption. But what we are showing is that maybe this isn't the case. Like Thunderella can tolerate minority corruption, and yet we are still very fast. Okay, so this is a very simple little protocol, but it's very powerful. Okay, before I conclude, I want to mention that simplicity is your best friend in these large-scale distributed systems. All right, so our company is hiring. If you are interested, you should contact us. If you are the app developer wanting to use our platform to develop the next generation or the more sexy Thunder kitties, you should also contact us. Thank you very much.